Okay, in this video we will see keeping a Colab running during training. When training is Google Colab, it's important to understand the runtime limits so you don't lose progress. First, if you the Colab browser tab in inactive, in the front end disconnects, but the training continues in the background. You can simply click reconnect to resume access. In this figure, in this Colab reconnect button will be shown. Second, there is a 19 minutes inactively timeout. If you don't interact with the notebook for the long, the Colab will shut down the runtime and all unsaved work is lost. To avoid this, click or scroll at least once every 19 minutes. Colab also a 12 hours minimum runtime. So very long training sessions may be stopped automatically. For our projects, once the tensor board shows 80,000 training steps, the model is completed and ready for deployment. And the preparing it for deployment is much faster than training. Freeze the graph. Once the training is completed, the model's weights and biases are saved to checkpoint files. Every 100 steps, this file allows you to resume the training. If something goes wrong, you can view the collapse file browser by clicking the left sidebar button and the opening the content speech commands train by directory. In this figure, we can see figure the button that open the collapse sidebar. Next one, the collapse file browser showing a list of checkpoint files. A TensorFlow model is made up to two parts. One, weights and bias, and next one was computation graphs. It's used to model prediction, also called inference. We need to merge these two components into a single file. What is freezing? The freezing creates the static that combines the model graph and the trained weights, makes the model ready for inference. How to freeze the model? Run the scripts in your Google Colab notebook that start checkpoints to final training checkpoint. Output files the name of the fonts. After running this, we all file called TinyCon, which is your fully trained TensorFlow model. Next step, we need to convert this fonts model with TensorFlow Lite format so it can run efficiently on mobile and embedded device. Convert to TensorFlow Lite. Once the first the TensorFlow model, it will be PB file. The next step is convert to the TensorFlow Lite format. This format is optimized for the mobile and embedded device, it making a much smaller and faster to run. To perform the conversion, we will use tool called Toco. Toco means TensorFlow Lite Converter, which is turns the fonts graphs into a TLF Lite file. Key details. The input and output files locate specified and the context during training and the input shapes because dealing with the one input sample at the time. In this checking model size, the model ends up with very small, just around 18 KB, making ideal for the low resources environment like microcontroller. Create the C array. It runs actual hardware. It's like an embedded system or microcontroller. We need to convert the file into a C source file and involve the binary file into a C array, which embedded system in the firmware. What's the step? Converts the model file into an array of unsigned characters. Next one, length of the array. Okay. Next, we will see the using the model in your project. After the training and converting your TensorFlow Lite model to the you are already integrated into your embedded applications. It involves the three key updates. Once training is complete, we need to replace the old model with a newly trained one inside our project file. The process is straightforward. First, locate the file called microfutures training.con microfutures model data.ccc. That exam name may vary depending on your platform or IDE. This file contains the model data array. Next, open the tinycon file.cc file which holds the new model represented as a C array. Copy only the array contents everything between the query breaks and paste into the exiting array inside and keep the original variable number. Finally, the update of model length variable with value from the bottom of TinyConCSV. Don't change the declaration itself, only the content and size. Update the label names. You likely trained your model with custom labels like on and off. Is the update the label list to reflect the exact words in using your training session. These labels are what the model will recognize in real-time inference. Customized command actions. Now that your model can recognize the new words, you all want to define what happens when you hear them. Locate and edit. Add or update code that defines what the action to take on off its detector. Example, turn on an LED activates the motor, etc. This is where the connect the voice recognition to real world functionality. Next, we will see about updating command respond.cc. Purpose of command responder.cc. This files control what your device does. It will be detect the specific keywords. Previously, it was set up to respond yes by turning on the LED. Now it will be make smarter so it can turn the LED on means when you say on. If the turn LED off when you say off. What to update? In this Arduino version, found in the Arduino by command responder. If the old behavior, the code check the if detected starts with yes and turn on the LED. Now new behavior. You will change it to check if the word is on, the turn the LED on. If the word is off, the LED will be turn off. You do this checking the first and second letter of the word. On means O and N. Off means you will begin with O and F. Final behavior. Say on. Turn LED turn on. Say off. LED turns off. The model works a peek inside. The model works a peek inside. All through, we often treat the model as the black box, just giving it audio and receiving a prediction. It helps to understand how the input is actually prepared. Raw audio is not the suitable for machine learning. For the example, a 1 second audio clip recorded at 16 kHz produce the 60,000 raw numbers that far too complex and unstructured for the model to learn from directly. Instead, we will apply the future generations which transforms the audio into a 2D grade of values. This grade is known as spectrogram or sometimes it's the mil frequency capstral coefficients. You can think it's like the black and white images that shows how the frequency energies change over the essential unique fingerprints. And to develop the and institute to the why the easier of our model to deal with pre-processed input, let's look at original raw represents of some audio recordings as written in the figures. In the images tab of the TensorFlow. And we can see the waveform of an audio recording of someone saying yes, and in another figure waveform of an audio recording of someone saying no. In down the figure the spectrogram of an audio recording of someone saying yes and the spectrogram of an audio recording of the someone saying no. It's the it's the different variations of recordings we are get the images. And what is the neural networks is? This 2D grid like an images to watch actually goes into the model. Because of the visual likes format, we can converge neural networks. The same kind used to image recognition. The model scans the grid and learns patterns that match certain words like on and off. What happens inside? Convolutional layers looks the features like pitch, tone and timing in the audio. These futures are passed through more layers, gradually building the stronger understanding. In the end, the model gives the confidence score for each label, like how likely it thinks the herd, on, off, or something else. So in the short, we can see the audio after future grid like as an image and the neural network. And the next one, last is word predictions. Why use spectrogram instead of raw audio? Instead of feeding a raw audio directly into a model, we use the spectrogram and the several reasons for this. First, spectrograms are easier to interpret. This display frequency patterns visually. So words like S produce shapes such as inverted L that both humans and models can recognize more easily than waveform. Second, they provide the dimensionality reductions. A raw waveform contains around 60,000 values per seconds, while the spectrogram compares with this down about 1960 values, a more compact and meaningful representation. Third, the spectrogram make models more efficient, reducing workload for embedded system. While the alternative like WaveNet can process raw audio directly, they requires for more computations, making them less suitable for microcontrollers. Okay, I will stop here. We will see the next video.